The other instruction that we have in this RST category is the trap instruction, which is a not maskable interrupt. So, that is a non maskable interrupt. So, you cannot mask it off, but these instructions these interrupts RST 5.5, 6.5, 7.5. So, these are hardware interrupts. So, these hardware interrupts so they are maskable. Okay. So, we can mask off these interrupts. So, we will see how they can be done, and they are also vectored interrupt because the addresses are fixed. Okay. So, they are automatically vectored as per this table is shown. So, they are masked so this masking of this interrupt 5.5, 6.5, 7.5, it can be done at two levels. One level is via the interrupt enable flip flop and the EIDI instruction. So, that is one possibility. So, you can set the EIDI instruction, you can use the EIDI instruction to change the interrupt enable flip flop, and all the maskable interrupts will get masked. So, if you put the DI instruction. So, this interrupt enable flip flop, so it will control the whole maskable interrupt process, and also you can individually mask out the interrupts, like. So, there are individual controls, individual mask flip flops are available, and you can control individual interrupts that way. So, EI or DI, so DI instruction will mask off all the interrupts, okay, all the maskable interrupts, but you may want that only say 6.5 be masked. So, 5.5 and 7.5 should remain. So, how to do this thing for that purpose? So, we have to follow some other technique. We have to set reset the interrupts corresponding to individual lines. Okay. So, this is the diagram that shows the situation. So, we have got this flip flops mask 7.5 or M 7.5, M 6.5 and M 5.5. So, if these bits are made 0, so you see that this is inverted here. So, this bit is so if say 6.5, this bit is 0. So, you will get a 1 at the input of this AND gate, and then this interrupt enable flip flop is there. Suppose this bit is 1. So, this is 1. Now, if that 6.5 interrupt comes, then that interrupt is allowed to reach the processor. So, this is actually going to the processor. Now, if this bit is set to 1, if M 6.5 flip flop is set to 1, so that is the 6.5 will be masked off, because this AND gate will get an input of 0. So, whatever be the value of RST 6.5, so it will not reach the output. So, we have got this mask flip flops M 7.5, M 6.5 and M 5.5 for masking out these interrupts individually. But for INTR, we do not have this individual masking. So, INTR can be masked off by this interrupt enable flip flop only. Okay. So, through the EIDI instructions only. So, they cannot be it cannot be masked off otherwise. This RST 7.5 flip flop. So, there is another RST 7.5 interrupt, it has got another flip flop that we will see later. So, this is basically keeping the memory, like see this 6.5, 5.5 etc. So, these interrupts. So, you see that if this interrupt has to be sensed, then the interrupt line must be active for that 17.5 T cycle T states, whereas for 7.5. So, since this is a flip flop, so if this interrupt occurs, then the value will get latched here. So, when the processor checks at the end of that 17.5 clock cycles, then also it will find that flip flop value to be equal to 1. So, that interrupt will be sensed. Okay. So, this gives us some special facility with the RST 7.5 flip flop. So, that is it can be of much shorter duration than this 6.5, 5.5 and INTR pin. So, we will come to that later. So, the interrupt process first then as far as this interrupt process is concerned, first of all the process has to be enabled through the EI instruction. If EI is not executed, then that interrupt enable flag may be a flip flop may be 0. As a result, none of the interrupts will be reaching the processor. And the 8085 just like that the non-vectored interrupt, that is like that INTR. So, here also 8085 will check the interrupt during the execution of every instruction, and if there is an interrupt and the interrupt is enabled by the interrupt mask. So, this is the additional thing that we have here. It will check that M 7.5, M 6.5, M 5.5 flip flop, and then only it will say that the interrupt is received by the processor. So, it will the processor, if that flip flop is 0, if the flip flop value is 0, then the processor will sense that interrupt and it will complete executing the current instruction and reset the interrupt flip flop. The flip flop will be reset and the processor will execute a call instruction, and this call instruction is a hardwired call. So, now for unlike that INTR where the device had to provide the vector address through some special arrangement of buffers and all that. So, here we do not need all those things. Here the processor it is fixed, the addresses are fixed. So, processor will directly go to the corresponding address, and that address is also obtained in the similar fashion like 5.5 if it is RST 5.5. So, 5.5 multiplied by 8. So, it will be 44. So, it will go to the location 44 and start executing from there. So, that way it continues. So, when the processor executes the call instruction, it saves the address of the next instruction on the stack. The processor jumps to the specific service routine, and the service routine must include the instruction EI to re-enable the interrupt process. So, these are same as that INTR interrupt process. Once the only the sensing part is different, and then there should be the rate instruction at the end of the service routine, so that the execution will return from the ISR. Now, since the masks are there, so we must know a technique by which these masks can be manipulated. Okay. So, one way to manipulate that interrupt enable flip flop is through the EI-DI instruction. That interrupt enable flip flop, that particular flip flop will be modified by EI or DI, but these individual masks for 5.5, 6.5 and 7.5, they are manipulated using the SIM instruction. So, there is a special instruction SIM which stands for set interrupt mask. Okay. Using this same SIM instruction, we can manipulate this setting of this mask flip flops. So, this instruction, it will take the bit pattern in the accumulator and applies it to the interrupt mask enabling and disabling to the interrupt mask, so that will result in enabling and disabling of specific interrupt. So, it will for using that instruction, so first of all we have to set the accumulator to a particular bit pattern, and after that when the SIM is executed, so individual bits of the accumulator, they will have some special meaning as we shall see. Then this accordingly those flip flops will be set to different values, and this mask patterns will be set. This masking of the flip flop will take place. So, this is the line. This is the diagram that shows how this individual bits of the accumulator will be interpreted by the SIM instruction. Now, there is one thing that this SIM instruction also helps in other operation which is known as the serial data transmission. So, we will see it after some time. So, the first two bits SDO and SDE, so they are for serial data input output type of operation. Okay. So, for our discussion now, so these two bits are of no use. So, so if this SDE bit is set to 0, so it will ignore this SDO line. Okay. So, for our discussion for the time being, this SDE line serial data enable, so this line will be 0. So, this bit will be 0, so that this SDO bit setting does not have any meaning. Okay. Then this bit number 5 is not used by the in this process. So, this is, it can be any arbitrary value, do not care value. Then remaining 5 bits, so they are used to control the flip flops. Okay. So, this M7 5.5, so this is the reset mask, reset 5.5 mask, this is RST 6.5 mask, this is RST 7.5 mask. So, if this mask bit is 0, that means we want to set the interrupt to be available, and if this mask bit is 1, then we want that the interrupt should not be available. Okay. The interrupt should not reach the processor, and whether we want to set this mask bit or not, so that is done by this MAC bit. So, mask set enable. So, if this bit is 0, so it will ignore bit number 0 to 2, and if this bit is 1, so it will set the masks according to the bits 0 to 2. Now, you see that there is so since the same instruction, so it is used for both serial data transmission and this interrupt masking. So, that is why we have got two guards actually. So, the SDE is one guard. So, that is useful when you are doing only serial data transmission. So, then that bit will be set to 1, and if you are not doing that, then this bit will be set to 0. Similarly, if you are using this SIM instruction for serial data transmission and not for mask setting, then this MSC bit should be set to 0. So, that if this MSC bit is 0, then this mask setting does not have any meaning. So, then this then we can use it for serial data transmission by setting this SDE line to 1. And if we really want that this mask bit will be set, then we should make this MSC bit 1, and then this pattern will be set to the mask flip flops of the interrupts. And this R 7.5, so this is the this setting of this RST 7.5 flip flop. So, in this diagram that we have seen, so this RST 7.5, so this flip flop, so this flip flop can be set by getting that RST by setting this R 7.5 bit. So, the accumulator has to be set a value as per our requirement, and then the same SIM instruction has to be executed. So, this is the details that bit 0 is the mask for RST 5.5, 1 is the mask for 6.5, 2 is the mask for 7.5. If the mask bit is 0, then the interrupt is available. If the mask bit is 1, the interrupt is not available. So, it is masked off. Bit number 3, it is used for enabling, it is an enable for setting the mask. So, if this is 0, then the mask setting will be ignored and the previous settings will continue, and if the bit is 1, then the new settings will be applied. Okay. And this SIM instruction, it is there are multiple purposes, as I have said. So, the serial data transmission is also used here. So, bit number 3 is necessary to tell the microprocessor whether to use the interrupt, set the interrupt mask or not, and similarly that SDE line, so that is used to say whether we are going for serial data transmission or not. Now, this RST 7.5 is the only interrupt that has memory. So, as I was telling, so that it has got a flip flop R 7.5. So, that is for latching that occurrence of that interrupt. So, if a signal on RST 7.5 arrives while it is masked, a flip flop will remember the signal. So, it might be that RST 7.5 is currently masked off, but still if the interrupt occurs, that flip flop value will be set to 1. And when this RST 7.5 will be unmasked, then the processor will be interrupted even if the device has removed the interrupt signal, because that flag is set, that flip flop is set. So, when this after some time if the interrupts are enabled, then this processor will get that interrupt. So, this flip flop is reset when the processor responds to the 7.5 interrupt. So, this is basically the purpose, like if we are doing something and we were busy, the processor was busy doing something at which this interrupt has occurred 7.5. So, it will remain latched in the system, and later on the processor may like to respond to that interrupt. Okay. So, this facility is provided, and it is not provided with other flip flop, other interrupts like 6.5 and 5.5. So, only with 7.5 it is there. So, if you want to reset this bit, so if you want that the processor should not get the interrupt, then you can reset this 7.5 memory by using this bit 4. So, bit 4 of the accumulator in the SIM instruction allows explicitly resetting the 7.5 memory even if the microprocessor did not respond to it. So, in this slide, so if you this is reset 7.5. So, if you keep this bit as 1 and after that execute a SIM instruction, then the RST 7.5 flip flop will be cleared. Okay. So, even if when the processor was busy, the interrupt has occurred and the flip flop is set. So, instead of going into the interrupt service routine, so you may just like to reset that flip flop, so that we do not respond to the interrupt. Okay. So, for that purpose, so we can keep this RST 7.5 line 1 and execute the SIM instruction. So, it can also be used for data transmission, as I said that serial data, the SID and SOD pins are there for 8085 for serial data transmission. Now, this bit 6 will be used to tell the microprocessor whether or not to perform serial data transmission. If it is 0, then do not transfer serial data. If it is 1, then when the SIM is executed, then this SOD line has to be the value to be sent on the SOD has to be placed on the bit 7 of the accumulator. So, whatever be the value at bit 7, so that will go to the serial data out line, and bit 5 is not used by the SIM line. So, we take an example. Suppose we want to set the interrupt masks of so that this 5.5 is enabled, 6.5 is masked off, and 7.5 is also enabled. So, for that purpose we have to first identify the content of the accumulator that it should be there. So, we want to enable 5.5 and 7.5. Okay. So, we want to enable 5.5. So, bit 0 should be equal to 0. We want to disable 6.5. So, bit 1 should be equal to 1. We want to enable RST 7.5. So, bit 2 will be equal to 0. Now, we have to allow this mask setting, whatever mask we are setting, this 0 1 0 should be allowed. So, accordingly this MAC bit should be equal to 1. So, this bit 3 is made equal to 1. RST 7.5 is enabled, and we do not want it the flip flop to be reset, that is if some interrupt has occurred. So, this flip flop that interrupt should be there. So, do not reset the flip flop. So, this R 7.5 bit is set to 0, bit 5 that is do not care, that is not used, and we are not going to use for serial data transmission. So, bit 6 and bit 7 they are made 0. So, this is the bit pattern that we have to set in the accumulator. So, that is done here. So, this pattern is 0 A. So, this most significant byte is all 0, and the next byte is 1010. So, that is A. So, first we enable interrupt. So, it will enable all interrupts including INTR. Then we move the pattern 0 A to the accumulator. So, that is done by the MVI instruction MVI A, 0 A. So, it will set the accumulator to the proper pattern that we want, and then execute the SIM instruction. So, when the SIM instruction is executed, this particular bit pattern. So, this will be setting the appropriate flip flops and masks, and the desired functionality will be achieved, that is 5.5 and 7.5 will be enabled and 6.5 will be masked off. Next important thing that we have is about the triggering level. Okay. Now, you see that if you look into classification of interrupts, then one classification that we have is that of triggering level. So, trigger level of interrupts. So, they can be on that basis. So, we can classify it into two categories. One is level triggered, and another is edge triggered. Okay. Just like flip flops, we have level triggering and edge triggering. So, here also we have got level triggered and edge triggered. So, level triggered means if this is the processor and this is the line, the interrupting line that is there. So, if it is a level triggered interrupt, then for the line to be sensed, the level of the interrupt should be high. So, it is like this. So, the high value will be sensed by the processor. On the other hand, edge triggered means the edge will be sensed. Okay. So, this rising edge will be sensed as the interrupting point. So, you see that for this thing to happen, for this rising edge sensing to happen, so we should be able to latch the occurrence of this particular event. Now, so far whatever we have said that 5.5, 6.5 they do not have any separate latch or memory, but 7.5 has got a latch associated with it. So, this 7.5 is basically an edge triggered flip flop, edge triggered interrupt, because when that interrupt occurs, then the value will be put into the that latch will be set accordingly. Even if that line goes low after some time, say after some time it goes low. So, this rising edge, so this will be remembered by the flip flop, and this triggering will take place. Okay. So, this when a positive edge appears on the RST 7.5 line, a logic 1 is stored in the flip flop as a pending interrupt, and now this value is stored in the flip flop. So, it does not, the line is no more needed to be kept high. Okay. So, the processor can check the interrupt that is to be recognized. So, so it checks whether that any interrupt has occurred, and accordingly it can do that, and the line must go to 0 and back to 1 before new interrupt has occurred. So, this is another good thing. Like otherwise, for level triggered interrupt, what happens is that if the processor, as soon as the enable line, the EI bit is executed, then if the value of that line is still 1, that interrupt line is still 1, so that will be sensed as another interrupt. But in case of edge triggering, so it is based on the edge. So, if the another edge has not come, that is in between the line has not gone down to 0 and then again it has risen to 1. So, if that has not happened, so that will not be taken as a new interrupt. So, this way the edge triggering may be helpful. Then this RST 6.5 and 5.5, they are level sensitive, and the interrupting signal must remain present until the processor checks for the interrupts. Okay. So, this way this triggering level, so we have got various combinations, like INTR is also a level triggered interrupt. So, we have got all these combinations available in the 8085 processor. So, depending upon the type of device that you are going to connect, so you can have this level triggering or edge triggering. Accordingly, you can choose the type of interrupt to which it should be connected. So, next part is sometimes we would like to see what is the current mask setting, because maybe we do not want to disturb the current mask setting, only change it a bit. So, we do not want to put a completely new setting, but just want to change the bit. So, for that purpose, so there is another instruction called RIM, which reads as read interrupt mask, RIM, read interrupt mask. So, what it will do? It will load the accumulator with an 8-bit pattern showing the status of each interrupt pin and mask. Okay. So, what happens is that the RST 7.5 memory, so that R 7.5, so that comes to the bit number 6. Then this 6.5 pin status, so that will come to P 6.5, this 5.5 pin will come here. Then this interrupt enable flag, so that will come as bit number 3, and this mask flip flop content M 7.5, 6.5 and 5.5, they will come to the bits 2, 1 and 0. Then this bit number 7, so this is reserved for serial input data or serial data input. So, this RIM instruction is also used for serial data input. So, the SIM was used for serial data output. So, RIM is used for serial data input. So, if we are not using that, then that bit has to be discarded, but otherwise the rest of the bits, so they will give us the current interrupt mask setting in the processor, and this will be useful. Like if you want to change the mask setting slightly without disturbing others, so you can use this particular situation. So, this is the thing, that this RIM setting, so this will be affecting the thing, the previous diagram. So, it is shown like this. So, if the serial data line, so whatever is available in the SID pin, so that will be available in the SDI bit here. Then if some RST 5.5 interrupt is pending, then this P 7.5 bit is 1. If 6.5 is pending, then P 6.5 is 1, and this is 7.5 is pending, then I am sorry. So, this is this diagram is slightly so this P 7.5, 6.5 and 5.5. So, 7.5 is at bit number 6. So, 7.5 should be at 7.5 is at bit number 6. So, this should be 7.5, not 5.5. So, this should be 7.5, this should be 5.5. So, 5.5, 6.5 and 7.5. So, they are storing the corresponding pending bits. Then this IE bit, so this will store whether the interrupt enable flip flop content, so that will be stored here, and this will store the mask bits. Okay. So, that way I can, through the RIM instruction, I can get this complete status. So, this bits 0 to 2, they show the current setting of the mask for the RST 7.5, 6.5, 5.5. So, they will give you the content of the mask flip flops. They can be used by a program to read the mask setting. Then bit 3, So, this is used to show whether the maskable interrupt process is enabled or not. It will return the content of the interrupt enable flip flop, and it can be used to used by programs to determine whether interrupts are enabled or not. So, if you want to check whether the interrupts are enabled or not, so you can execute a rim instruction and then check bit number 3 of it to see whether the interrupts are enabled. Bits 4 to 6, so they are actually for so the pending interrupts, as we said, for 5.5, 7.5, 6.5 and 5.5. 4 and 5 they return the status of RST 5.5, 6.5. Bit 6 will return that the RST 7.5 memory flip flop. Okay. So, and this bit 7 is for serial data input. Okay. Then the rim instruction, so for the serial input data, whatever SID pin, whatever data is coming, so it can be it will come to bit number 7. Now, so we can since there are so many interrupt lines, there are 5 interrupt lines. So, interrupt may occur during ISR and they can remain pending. So, using the rim instruction we can check whether any interrupts are pending, and if we do not want to respond to those interrupts, so accordingly we can clear those flip flops. Okay. So, this is the advantage of being able to find out the interrupts of RST say 7.5, 6.5, 5.5 without having to enable the low level interrupt like this INTR. So, we do not want to reset enable INTR. So, we want to just access other interrupts. So, we can do that. So, this is an example to show how to set mask to enable RST 6.5 without modifying the masks for 5.5 and 7.5. So, 5.5 and 7.5 whatever setting is done, that should continue. We just want to enable the RST 6.5 bit. Okay. So, how to do this? So, we have to first execute a rim instruction to know the current setting of 5.5 and 7.5, and then we have to use sim instruction after modifying the accumulator. Okay. So, we can do this thing. So, suppose the current setting of RST 5.5 and 7.5 they are enabled and the interrupt process is disabled. So, this is the current setting. So, if you execute a rim instruction, you will get the bit pattern like this, because this 5.5 and 7.5, so they are enabled, 6.5 is disabled now, and interrupt enable is disabled. So, IE is disabled. Now, so after getting this pattern, so we have to now we want to set a new mask. So, this bit 4 MSC bit will be set to 1. So, that so we OR this content with the 08 hex. Okay. So, this content is ORed with 08 hex. So, this bit becomes set, and then we do an AND immediate with 0D hex. So, when you do this, so this will turn off the serial data, that is this SDE bit will be turned off, and we want to, but we do not reset that 7.5, we do not want to touch that is 7.5. Okay. So, that way the 7.5 will not be touched, this M 7.5. So, whatever be the value, so it is ANDed with 1. So, the value will be just coming here. Then this then 6.5 is turned off. So, 6.5 is this one. So, this M 6.5. So, this is 0 0 0 0, this is 1. So, this 1 is for this coming for this MSC, then this 7.5. So, it continues. So, 6.5. So, this bit is made 0. So, this will be ANDed with that, and accordingly we will get a 0 here. So, this process will this M 6.5. So, this interrupt was enabled. Okay. So, this interrupt was disabled, and then after this, so this interrupt becomes enabled, whereas the status of this 7.5 and 5.5 they remain unchanged. 6.5 it was disabled previously, now it becomes enabled. So, without touching other interrupts, so you can do set reset in the particular interrupt. Okay.